Linear systems is a very important concept in acoustics and vibration. So this presentation we will spend on introducing the concept of linear systems. We will meet two important concepts. First of all, of course, the linear system concept, and then a linear system model concept, where the system is modeled as an excitation, a path between the excitation and the response. We will illustrate the linear system concept with an example where we have this loudspeaker element, and suppose now we feed the loudspeaker element coil with an alternative current. Then, of course, the electromagnetic forces caused by the alternating current in the coil forces the membrane of the element to move back and forth. And that motion, membrane motion, will of course excite sound waves that propagate in the surrounding air. And if we measure now the sound pressure in a point somewhere in the air surrounding the element, we can conclude that the measured sound pressure will depend on a number of factors. And the measured sound pressure is what we call the response. And the sound pressure we measure will of course depend on, first of all, most importantly, the amplitude and frequency of the current that we feed to the coil. And this is called the excitation. It will also depend on the element properties, the size, for instance, of the element, and the stiffness of the membrane, and the weight of the membrane, and so on. It will also, of course, depend on the medium's properties. Now we have supposed that we have air, but if we change the air to another gas, fluid, or something else, the sound pressure we measure will, of course, change. Of course, the room properties, if we have this element placed in a room with limited size, the measured sound pressure will change if we change the room properties. That is the size of the room and the materials on the walls and ceiling of the room absorption. And finally, the measurement point position will of course also affect the measured sound pressure. So this last four factors is what we call the path between the excitation and the response. So these three parts, components, constitutes the excitation path response model of a linear system. And we need, of course, now a method, some kind of model, to describe how the response depends on the source properties, the excitation, and the path between the source and the response. And that is where this linear system model comes in. First of all, a linear system, the most important property of a linear system is that the response is proportional to excitation. And this property is sometimes called homogeneity principle. Secondly, the responses, if we have two excitations, is of course the sum of the responses to each individual excitation. This is often called superposition principle. And finally, a very important property is that the response cannot contain any other frequencies than the excitation contains. And this is sometimes called frequency conservation. In mathematical terms, we have a linear relationship that reads y, the output, is equal to the input x times a proportionality factor plus a constant m. So in this case, x should be the excitation and y the response. In sound, well, in acoustics and vibration, we have this relationship. The response at a certain frequency is a proportionality factor times the excitation at this particular frequency. So we have no constant m, and that is of course because a constant pressure is not sound. We define sound and vibration as something that varies with the time, so it cannot be constant. So we can exclude the m in sound and vibration linear system. So in our case here, x here is a system input signal, with the amplitude of the system input signal, the excitation amplitude, or the source amplitude. Whereas the y here is the system output signal amplitude at frequency f, of course, which is the same as the response amplitude. And the proportionality constant, h, is what we know as the frequency response function of the system. And that describes the path between the excitation and the response. And as we can see here, this is frequency dependent.